Okay. In the previous session, then we just finished open loop control system, its behavior, its definition, closed loop control system, its behavior, definition, block diagram and everything. And after that, I just give the transfer function analysis importance also, and the transfer function analysis importance, what it will do, what its role in the control system also we'll see. So now what we are doing is, then now you know the block diagram of the open loop control system and you know the block diagram of the closed loop control system. Therefore, now we will see the basics of the open loop control system, closed loop control system, which we already finished. Then we will see the mathematical equivalent model of open loop control system and mathematical equivalent model of closed loop control system. Why mathematical equivalent model? That's what I'm saying. Once if you have the mathematical equivalent model, you can understand the complete behavior of the system. So now before we start the mathematical equivalent model, then which we already in the transfer function analysis Laplace transformation explained. Now we want a basic formulas of the Laplace transformation, because those formulas are continuously repeated in our subject, which we already known that, but just give a summary of that. Okay. So then you tell me, what is the Laplace transformation of e power minus at? You already know that 1 by s plus a. This is in time domain, which is exponentially decaying. Now e power plus at, now whose Laplace transformation is 1 by s plus a. E power plus at, whose Laplace transformation is 1 by s plus a. Now this is nothing but exponentially increasing. Now this is exponentially decaying and this is exponentially increasing with respect to time, and this is in frequency domain, because these few formulas which are completely repeated in our subject. That's what I just give an overview of this particular formulas, which are very important, which are known to you also. Sin bt, whose Laplace transformation is, you know that, b by s square plus b square. Cos bt, whose Laplace transformation is s by s square plus b square. And Laplace transformation of t power n, which is n factorial by s power n plus 1. Now these are the few basic formulas which are continuously repeated in the subject. That's why all the formulas, just once we just go through one look, such that which is very easy for our further mathematical analysis of the subject. Now first you take these formulas. Okay. And Laplace transformation of e power n into e power plus at. Now any exponential term multiplied with any signal we just forget about this exponential term. T power n Laplace transformation is n factorial by s power n plus 1. T power n Laplace transformation is n factorial by s power n plus 1. Once this is f of t, now replace, this is f of t and this is whose Laplace transformation? F of s. Now replace s by e power at means where there is s, replace s by s minus a. Means what? Where there is a s, replace s by s minus a, which means that now this is n factorial by s. S means e power at means s minus a whole power n plus 1. Exponential term multiplied with any signal. Now assume this is f of t. First write its Laplace transformation f of s. Where there is f of s, replace s by s minus a or s minus a or s plus a. If this is e power minus at, then this is s plus a. Same. This is the same formula which we are used when any exponential term multiplied with any signal with respect to time. Now, for example, you can take like this: e power plus at into sine bt. Now, what is sine bt? Sine bt, which is nothing but b by s square plus b square. B by s square plus b square. Where there is a s, replace s by e power at means here this is s minus a. Now this is e power plus, therefore this is s minus. If this is e power minus at, then this is s plus. Same. E power plus at into cos bt. Cos bt's Laplace transformation, which is nothing but s by s square plus b square. Cos bt means s by s square plus b square. Where there is s, replace s with e power at means s minus a. Now this is e power minus at, therefore this is s plus a, this is s plus a. So these are the basic formulas which we are continuously repeated in the subject. That's why I am taking all these basic formulas which are very familiar to you, because in different subject also you can study this Laplace transformation. Therefore, these are the formulas which are continuously repeated. That's why all these formulas I am doing here, I am taking here. So now you have basic formulas and Laplace transformation and transfer function analysis importance. Therefore, now we will see. Now in this, we are here at open loop control system. Now here we will see now mathematical analysis of open loop control system. Now we are at this stage. Now we go to this particular stage. In the same manner here also, this is closed loop control system. We finish this one. Now here is from here to, now we will go for mathematical analysis of closed loop control system. Then you tell me, then who is supplied this mathematical analysis? Now, which is supplied by this mathematical analysis? That's what we start with previously. Now, this mathematical analysis and mathematical equivalent model, which is given by transfer function. Therefore, this, once you have this, you can easily find the transfer function of open loop control system. Once if you have this, you can easily find the transfer function of closed loop control system. So we will try to finish this two. We will try to finish these two because we know the open loop control system, we know the closed loop control system, and we want to see the mathematical analysis of open loop, and we'll find the transfer function, and we will see the mathematical analysis of closed loop, and we'll find the transfer function of closed loop, because we know the block diagram of open loop and closed loop. In such a situation, all these formulas and all these things are important. We'll just take this is the overview what we are going to be discussed. Okay, then we'll see the mathematical analysis of the open loop control system. Then first we will see the block diagram of open loop control system. We know that this is reference input controller, processor, controlled output, now this is a reference input. I am represented as R of t, reference input. This is controlled output, represented as C of t. This is fixed in our subject because our control system, this is the reference input and this is controlled output, which is C of t. And similarly, this is controller, this is having some gain G1, this is processor, this is also having some gain G2, and these two are connected in series. These two are connected in series, cascade. Therefore, what is the overall gain? The overall gain is nothing but G1 into G2. Now, let us assume this is some G of t. I am assuming this is overall gain of the control and processor. This is G1 into G2. Both are connected in cascade. And I am assuming this is some G of t. Therefore, this is input and this is output. And this is the direction of input to output. Now, this is called as forward path. Forward path is a path between input to output. Therefore, this controller gain G1, this processor gain G1, G2, and this is I am assuming as G of t. Therefore, can we call this is forward path gain? This is forward path gain. This is the open loop control system. This is open loop control system block diagram. This is open loop control system block diagram, input and forward path, and this is output. Therefore, now we want a mathematical analysis of open loop control system. For finding the mathematical analysis, we want to apply the Laplace transformation. Then see here, what is the Laplace transformation? Laplace transformation of R of t is R of s. Laplace transformation of G of t is G of s. Laplace transformation of C of t is C of s. This is a mathematical equivalent model. See here. Now the reference input, controller, processor, controlled output, all are gone, and this is a complete mathematical relation. This is a mathematical equivalent model of open loop control system. Therefore, this is a mathematical equivalent model of open loop control system. Once you have a mathematical equivalent model, then you can easily find the transfer function or not. Then what is the transfer function? Now see here. What is the transfer function? The transfer function is nothing but Laplace transformation of output by transfer function is nothing but Laplace transformation of output by Laplace transformation of input. The Laplace transformation of output to the Laplace transformation of input is nothing but the transfer function, which is nothing but only G of s. What is G of s? Only forward path gain. Therefore, this is nothing but open loop control system transfer function. Open loop control system transfer function, which is nothing but the Laplace transformation of output to the Laplace transformation of input, which is nothing but only forward path gain. Yes, this open loop control system consisting of only forward path. Therefore, the transfer function is also saying the same or not? Yes, this is the only forward path gain G of s, and this is the open loop control system transfer function. In the same manner, we can find the mathematical equivalent model of closed loop control system, and we can find the transfer function of closed loop control system also or not? Yes. Now, before we go for that, then first we will finish this open loop control system mathematical analysis. Then after that, we go for the mathematical analysis of closed loop control system, all these things. Therefore, this is the open loop control system transfer function. Can I write like this? The open loop control system transfer function. So, the open loop control system transfer function, now you can easily identify that. Sir, what is open loop control system transfer function? Whenever open loop control, this is open loop, that is open loop, nobody will give. You have to say that this is open loop control system. How can you can identify that this is open loop control system? You can identify this is open loop control system. Only there is a forward path gain. Am I not? Because in open loop control system, no feedback, nothing. No, there is only forward path gain G of s. Now see here. Now this is the open loop control system transfer function, only forward path gain. This is in frequency domain, this is in s domain. Therefore, can I write one equation in terms of s? K into 1 plus st1, 1 plus st2, and so on by s power n into 1 plus sta into 1 plus stb into and so on. Now see here. Now, sir, why you are writing an equation like this? Now, why you are writing an equation like this? That this is the open loop control system transfer function, which is a forward path gain. I write an equation in terms of s because this is in s domain. This is in s domain. But here there is some parameters are available. This is control system, a open loop control system, and it is having some parameters. The open loop control system, it is having the system behavior. The system behavior is depends upon the system parameters. Sir, what are the system parameters? Now here, Now here the k is there. Here k is nothing but control system gain. Here k is nothing but control system gain. Now here T1, T2, here T1, T2, TA, TB, T1, T2, TA, TB and so on. All these things are nothing but, now this is tau, which is nothing but control system time constant. Now see here, where this k is control system gain, where T1, T2, TA, TB and so on are control system time constants. Therefore, this is control system gain, this is control system time constant. These are control system parameters. These are control system parameters. What is the meaning of that? That control system parameters is nothing but, now the control system behavior, the control system response, the control system complete behavior is depends upon the control system parameters. The control system parameter is nothing but gain and time constant. Remember these 2 points which are very important. Any control system, whether open loop control system, closed loop control system, you just forget a minute, the control system behavior, the control system response, the control system complete analysis is depends upon the control system parameters itself. One is control system gain, another one is control system time constant. You ask me one question, sir, if I change the gain, then the control system behavior is changing. If I change the time constant, the control system behavior is changing. What is the answer? You tell me. When gain is changing, when time constant is changing, control system behavior is changing or not? You tell me. Answer is yes, definitely. Once the control system gain is changing, the control system behavior is changed. Once the control system time constant is changes, the control system behavior is changing. That you can have experience very soon. We will see the proof of that. Okay, there is no need to remember. We will change the gain and see the behavior. We will change the time constant and we will see the behavior. There is no worry about that. We will see the changing of gain, changing of time constant, and the system parameters we are changed, and we will see the system behavior is changing or not. We will observe. Okay. Therefore, these are the control system parameter. Which control system? Any control system, whether it is open loop control system or a closed loop control system. That is the control system parameters. The control system complete behavior is depends upon the control system gain and time constant. But here, this is which transfer function? Now here, I am talking about open loop control system transfer function. Therefore, this is open loop control system gain. And this T1, T2, TA, TB, T1, T2, TA, TB and so on are open loop control system time constant. For example, let us say if this is a closed loop control system, this is closed loop control system gain, this is closed loop control system time constant. That is the only difference. Therefore, whether it is open loop control system or a closed loop control system, the control system behavior is depends upon the control system parameters is nothing but gain and time constants. Therefore, now see here, this is the open loop control system mathematically equivalent model. This is open loop control system transfer function, and this is open loop control system parameters. First you take this one and we will move further. Okay. So this is control system transfer function, open loop control system transfer function. Now this is the gain and time constant are the control system parameters. Now see here, these are the roots and these are also the roots. Then if I multiply these roots, then we can get s square or s cube or s power 4 something. And we can multiply these roots s power n plus 1 or s power n plus 2 or s power n plus 3 and so on something. Therefore, this is polynomial in the numerator. Therefore, this is numerator polynomial. This is polynomial in the denominator. Therefore, this is denominator polynomial. Both polynomials are a functions of s. Both polynomials are the functions of s. Then this is the polynomial in the numerator. Therefore, numerator polynomial. This is polynomial in the denominator. Therefore, denominator polynomial. Now the question is, then we will take any one root of the numerator polynomial. Take any one root of the numerator polynomial. Then you can take any one root of the numerator polynomial. Then if you take any root of the numerator polynomial, then if you take any root of the numerator polynomial, then we will take a root of numerator polynomial. Root of numerator polynomial. What is the root of numerator polynomial? 1 plus s t1 equal to 0. Therefore, s equal to minus 1 by t1. Now see here, this is one of the root of the numerator polynomial. Now this is the root of the numerator polynomial. Now take this particular root and substitute in the transfer function. Then this is the root of numerator polynomial. Then this is the root of numerator polynomial. Take this numerator polynomial root and substitute in the transfer function, and this transfer function will become 0. Now s equal to minus 1 by tau 1. Take this one and substitute here. S equal to minus 1 by tau 1 means tau 1 cancel. 1 minus 1, which is equal to 0. Now what happened now the transfer function? Now the transfer function will become 0. Therefore, now this particular root, is defined as 0. This particular root is defined as 0. And this is a definition of 0 and represented by a symbol of circle. Represented by a symbol of circle in S plane. This 0 we can represent it by a symbol of circle in S plane. Then what is the definition of 0? Now I am saying, what is the definition of 0? Definition. What is the definition of 0? A zero is the root of numerator polynomial. A 0 is the root of numerator polynomial, which is a function of time constant, which makes the transfer function 0. A 0 is the root of numerator polynomial, which is a function of time constant and make the transfer function 0 and represented by a circle, the symbol of circle in S plane. Therefore, sir, why you take this one? You take this one also. What I am saying, root of numerator polynomial. Then you take the second root, 1 plus st2 equal to 0, s equal to minus 1 by t2. Again the transfer function will become 0. Therefore, then what is the simple definition? The simple definition is, the standard definition is a root of numerator polynomial, which is a function of time constant and make the transfer function 0, and that particular 0 is represented by a symbol of circle in S plane. And a easy manner, this fellow is also called as 0. This fellow is also called as 0, which means that all the numerator polynomial roots, easy definition, simple definition, all the numerator all the numerator polynomial, all the numerator polynomial roots are called as zeros. All the numerator polynomial roots are called as zeros. Am I right or not? Therefore, these are the numerator polynomial roots. Therefore, this is called as zeros. But this you can consider in which control system? This is in which control system? Open loop control system. Therefore, you put a name. This is open loop zeros. That's it. Open loop zeros. And represented by a symbol of circle in S-plane. Then how to represent it? Then first you take S-plane. This is S-plane. Positive real axis, negative real axis, positive imaginary axis, negative imaginary axis. That's what first of all I am giving S-plane. Now what is your root? Your root is nothing but S equal to minus 1 by tau 1 plus j into 0. Why? Because what is S? S equal to sigma plus j omega. This is real part. This is imaginary part. This is your 0. This is real part. This is imaginary part. Now see here. This is the real part. There is no imaginary part. Now what is the real part? Yes, this is the real part. Which real part? Negative real part. Negative real part means which side? Positive side or negative side? Negative real part means come to the left hand side. Positive real part means come to the right hand side. That's what now in the previous session what I am doing is the S-plane is divided into 3 parts. Left hand side of S-plane, right hand side of S-plane, imaginary part of S-plane for this purpose only. Now this is a 0. Then there is only real part. Which real part? Negative real part. Once there is a negative real part, you come to left hand side. Once there is a positive real part, you come to right hand side. So whether it is a left hand side or right hand side, that is decided by the real part. You first see the real part and decided where it is. Therefore, this is the real part and your real part is negative. You come to left hand side and where it is? Only negative real part, therefore which lies on negative real axis with a symbol of circle with a value of minus 1 by tau 1. This is the definition of 0. This is the representation of 0 in S-plane. This is the definition of 0 and representation of 0 in S-plane. And then this is very simple definition. All the numerator polynomial roots are called as zeros. A 0 is a numerator polynomial root. 0 is a root of numerator polynomial which is a function of time constant, negative of reciprocal of system time constant, and which makes the transfer function 0 and represented by a symbol of circle in S-plane. Represented by a symbol of circle in S-plane. Now this is the definition of 0. First you take this 0's definition and just we will take another, we will see the another definition. Okay, So this is a numerator polynomial root. From that I can get one definition. Then now I am taking a root of denominator polynomial. Now I am taking a root of denominator polynomial. Now we'll see, take a root of denominator polynomial. What is the denominator polynomial? 1 plus STA is equal to 0. Therefore, S equal to minus 1 by TA. This is the root of denominator polynomial. Take any one root of the denominator polynomial. This is also a function of time constant. S equal to minus 1 by tau A. Now, which is a reciprocal of function of system time constant. Then if you substitute this particular root in the transfer function, if you substitute this particular root in the transfer function, what happens? Minus 1 by TA cancel, 1 minus 1 0, something by 0. How much? Infinity. Now the transfer function will become, infinity. Now see here, now the transfer function will become infinity. Now which is a root of the denominator polynomial, which is a function of time constant, negative of reciprocal of system time constant, and makes the transfer function as infinity. Sir, if I take this particular root, also transfer function infinity. If I take this particular root, the transfer function is infinity, and this particular root is defined as pole. This is the definition of pole, SP, and this is represented. Now 0 is represented by a symbol of circle, but pole is represented by a symbol of cross in. This is represented by a symbol of cross in S plane. This is represented by a symbol of cross in S plane. So what is the easy definition of pole? Then what is the easy definition of pole? Now see here, what is the easy definition of pole is, this is the definition of pole. What is the definition of pole? Then this root is called as pole, this root is also called as pole, which means all the denominator polynomial, all the denominator polynomial roots are called as poles. All the denominator polynomial roots are called as poles. Same, the pole definition is also same. What is a pole? SP, which is equal to minus 1 by TA. SP, which is equal to minus 1 by TA. Now see here also, there is no imaginary part, only real part. Now which real part? Negative real part. Then what I am saying, when there is a negative real part, now you first come to which side? Left hand side. Positive real part, negative real part, positive imaginary axis, negative imaginary axis. Then which real part? Negative real part. So if it is a negative real part, then come to left hand side. Negative real part means left hand side. No imaginary part, only negative real axis with a symbol of cross, in S plane. Therefore, this is the representation of pole, and this is a symbol of pole. This is a pole notation, and this is the pole symbol, and this is the definition of pole. Now what is the simple we call as? All the denominator polynomial roots are called as poles, but this is the poles in which control system? I am taking here open loop control system. Therefore, this is nothing but open loop poles. This is nothing but open loop poles. This is a simple definition of poles and zeros. In which control system? No, not only in open loop control system, in any control system, whether open loop control system or a closed loop control system, definition is same. All the denominator polynomial roots are called as poles in open loop or closed loop, any control system. All the numerator polynomial roots are called as zeros in open loop, closed loop system, control system, anywhere. Only the difference is, if you are talking about the open loop control system, this is called as open loop zeros. If you are talking about the open loop control system, now this is open loop poles. If it is a closed loop control system, closed loop zeros are closed loop poles. That is the only difference, because any control system is having control system parameters and is having a zeros and poles. Now this is a definition of poles and zeros now in the control system. Then this is a open loop control system, mathematical equivalent model, transfer function, system parameters, definition of zeros and definition of poles. Then you just take this one. Okay, then now up to this particular point of view, then you are very clear that what is system, control system, open loop, closed loop control system, poles, zeros. Okay, so how to represent it, the definition, how to represent the zeros and poles, you are familiar. Therefore we solve a simple problem, and based on that we can understand the another important parameter. Okay, therefore a simple question I am giving. Then I just take a few open loop control system transfer functions and locate the poles and zeros on S plane. This is the open loop control system transfer function, and locate the poles and zeros on S plane. This is our open loop control system transfer functions. Now see here. Now this is the few examples of the open loop control system transfer functions I am giving. Then locate the poles and zeros on S plane. Then if you see here, now this is S plane. S plus 1 equal to 0, S equal to minus 1. Minus 1, which is a 0 in the numerator polynomial, is represented by symbol of circle. Now S plus 2 equal 0, S equal to minus 2. S equal to minus 2 means this is the denominator now, which is equal to pole minus 2, because only real part is there, only real part, therefore only real axis. That too negative real axis, therefore only negative real part, therefore negative real axis. Now similarly, now this is S plane. S plus 1 equal to 0, S equal to minus 1. Only one point you remember, negative real part come to left hand side, positive real part come to right hand side. Forget about the imaginary part. Imaginary part is existing or not, that is the second case. First case is see the real part. S plus 1 equal to 0, S equal to minus 1. S equal to minus 1 means this is a 0 on the negative real axis. S minus 2 equal to 0, S equal to plus 2. Plus means positive real part. 0. Now, S plus 3 equal to 0, S equal to minus 4. S plus 3 equal to 0, S equal to minus 3. Means a pole is on the negative real axis. S plus 4 equal to 0, S equal to minus 4. A pole is on the negative real axis. Now, this is also pole. Denominator polynomial roots are called as pole. Now, this is pole at origin. This is one pole at origin. Now, come to here. Here is also now S plus 3 equal to 0, S equal to minus 3 is a 0. Now, S square plus 2S plus 2, S square plus 2S plus 2. If you find the roots, minus B plus or minus square root of B square minus 4AC by 2A. If you find the roots, these are the roots, which is nothing but minus 1 plus or minus J1. Because you know the formula, A square plus B, AS square plus BS plus C minus B plus or minus square root of B square minus 4AC by 2A. These are the roots. Then if you see here there is a imaginary part. But previous all the problems there is no imaginary part. But here there is a imaginary part. Even if a imaginary part is existing or not, then you just see only real part. What is the real part? Real part is only minus 1. Minus 1. Real part is negative. Real part is negative means you come to left hand side. Yes, real part is negative. Some of you are writing here. No, this is wrong. You write only on imaginary part if there is a no real part. If there is no real part, only imaginary part, then you write it on a imaginary axis. But it is having both real part and imaginary part, then you see the real part. Real part is negative, come to left hand side. And one imaginary part, negative real part, positive imaginary part. Negative real part and negative imaginary part. Negative real part, negative imaginary part. What is the negative real part? The negative real part and negative imaginary part. Now, which is minus 1. And 1 0 is at minus 3. And there is poles here. How many poles? Denominator means poles. How many? S square means 2 poles. Where is the 2 poles? 2 poles at origin. For visibility I write here, but no, at origin 2 poles. Okay. At origin there are 2 poles. Again here writing, no, that is not possible to visible. That's why I write here 2 poles at origin. Then these are the 3 examples, and these are the poles and zeros location in the S-plane. Then what we are conclude here? Then you tell me these are the poles and zeros location in S-plane. Now, how many poles at origin here? How many poles at origin? How many poles at origin? Then see here, sir, there is 2 poles at origin, there is 1 pole at origin, there is no pole at origin. Therefore, now see here, there is no pole at origin in this particular open loop control system. This is called as type 0 control system. There is one open loop pole in this particular open loop control system. This is called as type 1 control system. Then there are 2 open loop poles available at origin. Therefore, this is called as type 2 control system. One important parameter which is coming here, what is that? Type of the control system. One important parameter which is nothing but type of the control system. Again I am saying there are 2 open loop poles available at origin, therefore type 2 control system. There is 1 open loop pole available at origin, therefore type 1 control system. There is no open loop pole available at origin, therefore type 0 control system. Type 2 control system, type 1 control system, type 0 control system, then this is type of the control system. What is the definition of type? What is the type of the control system? Type of the control system. What is the type of the control system, which is very important parameter? The type of the control system, which is nothing but the number of open loop poles at origin. The number of open loop poles at origin, or the number of poles at origin. The number of poles at origin in open loop control system is called as type of the control system, which is very important definition here. Therefore, one important definition which here, type of the control system, the number of open loop poles available at origin, or the number of poles at origin in open loop control system is called as type. Therefore, if you observe or not, then what we are doing is, now this is the basics of the control system. This is the basics of the control system. In the basics of the control system, we just take open loop control system, and here mathematical analysis. In this open basics of control system, which we are taking mathematical open loop control system block diagram. From that, mathematical analysis is nothing but transfer function. From that, one important parameter we are taking type. In the same manner, we'll take a closed loop control system and that block diagram, from that mathematically equivalent model, and from that transfer function. From that also we will take another important parameter. What is that important parameter, and how the mathematical analysis of a closed loop control system, that we will see in the next session. Now this is a one important parameter which is play the important role in the case of designing a control system. That important parameter is nothing but type. Okay, we just take of all these things. Then in the next session we will see the closed loop control system behavior, and what is the parameter which is coming in the closed loop control system also we will see.